Assalamu alaikum and welcome to lecture number 12. In this lecture we are going to discuss just two examples related to the previous topic that that was the properties of the Z transform, and the rest of the lecture will be we will be discussing the finding inverse Z transform, that is finding the time domain signal given the mathematical expression of the Z transform along with the region of convergence. So a few more examples on properties of the Z transform. So here we are given x of n and we need to find the uh, Z transform of this signal. So we know that a Z transform of cos omega naught and u of n is given by, so the Z transform you can find it for cos omega naught and u of n equals to 1 minus cos omega naught Z inverse over 1 minus 2 cos omega naught Z inverse plus Z power minus 2, right? So now using the scaling property in Z domain or Z transform, you understand it simply replace z by z over, here the exponential is a, so z over a, right? So if z inverse, this one z inverse is replaced by z over, not z inverse, right? So z is replaced by z over a, so that means it will become z power minus a over a power z power minus 1 over a power minus 1, so a power minus 1 will come here, so you get this thing. Similarly for the denominator case also, this, right? So you get this expression and you understand the ROC will be, uh, in ROC you also replace z by a, or you can also say z absolute should be greater than a absolute. So this is how you can use. If you have any confusion, you can ask me in the live session. Similarly, we have another example. We have x of n which is equal to u of minus n. So you have learned the time reversal property. So u of n has z transform 1 over 1 minus z uh, minus 1, and it has region of convergence of z absolute greater than 1. So using the time reversal property, in time reversal property you replace z by 1 over z, so this is already 1 over z, so it will become z, and the region of convergence ROC, it will be 1 over z, right? So this is z inverse or 1 over z and the same. So hope this gives you idea. So that's all for the Z transform. From this point onward, we'll talk about the inverse Z transform. So this is the equation for finding the Z transform, or the analysis equation of the Z transform, and the inverse Z transform can be found using this equation, which is also called the synthesis equation or formula for the inverse Z transform. However, for typical kinds of sequences and Z transforms that we will encounter in the analysis of discrete time LTI systems, less formal procedures are sufficient, and preferred techniques based on the rather than this equation. So we'll be exploring about the other methods for finding the inverse Z transform. They are sufficient and they are preferable techniques. So the first method, or the first technique we are going to consider, is the inspection method. So I hope you can recall that in the while we were doing the Fourier transform, right? In that case we also used the method called the inspection method. In this method we know that for a right-sided exponential sequence a of n, u of n, it has a Z transform of 1 minus this one, right? 1 over 1 minus a Z inverse, and it has region of convergence which is Z absolute should be greater than a absolute. So if we need to find the inverse transform of something like this, so if you compare this one with the this transform, so you can easily say that basically A is 1 by 2, right? So this one, so we can recall the Z transform pair above, and we can find the inverse Z transform by inspection as follows, right? So by comparing with this generalized equation and knowing the ROC, which is for the right-sided sequence, because absolute of Z is greater than A absolute, so that means we can straight away find the inverse Z transform of this expression, which is equal to x of n equals to 1 over 2 power n u of n, right? So straight away, right? So if you have any confusion, for me it's quite straightforward, because you are already familiar with the inspection method, but the difference is only there you use it for the discrete time Fourier transform, and now we will be using it for the discrete time signals, another transform that is called the Z transform. So just by comparing the transform pair, we can easily notice that AFN is simply 1 by 2. Similarly, for a left-sided exponential sequence, we have found the Z transform of the signal, right, which is equal to 1 over 1 minus A Z inverse, and Z absolute is less than A absolute. So when Z absolute is less than this one, so you understand this will be left-sided sequence. So once knowing the ROC and the generalized expression, now if you are given this equation, this expression and the ROC, we can easily tell that this sequence will be the left-sided sequence, and the inverse Z for this one using the inspection method, it will be something like here. For A, we can replace A by 1 by 2. So we have minus 1 by 2 to the power n u of minus n minus 1. So I hope this gives you idea that's the inverse Z transform. So it's quite straightforward, right? So inspection method is quite straightforward for, right? Now we have to this problem I have already given you as a homework, so perhaps you must have done it. Again, that's very simple to find the convolution of x1, which is equal to this one, and x2, which is equal to this one. So you know, convolution is a tedious operation and you require a lot of effort. So the easy procedure is, because you have read about the Z transform and you know properties of Z transform, so based on the properties you have studied, that you know that in time domain, if two sequences are convolved in frequency domain, they are just multiplied. So you take the Z transform of this signal x1, and then again you take the Z transform of x2. Once you have both, you multiply the two and you get the Z transform of the product. Okay, so this is your x1. Okay, you understand, for impulse we have Z transform equals to 1. This is again impulse scaled by a factor of 2, and Z is linear operation, so we can scale it by a factor of 2, and because this is the impulse of n minus 1, so the transform will be just multiplied by Z minus 1. Again, this is 2 units shifted, no scaling, so it will be again Z power minus 2. Similarly, for these impulse of n, we have 1. For impulse of n minus 1, we have Z inverse. For impulse of n minus 2, we have Z power minus 2, Z power minus 3, Z power minus 4, and Z power minus 5. So if we multiply the two sequences, we obtain x of Z, and x of Z equals to product of the two x1 of Z into x2 of Z. So it will be, if you multiply it, you can easily get this simplified answer. Okay, so because now you know the answer for the inverse Z transform, the Z transform, you have found. Now the simply if I take the inverse Z transform for this one, so we can obtain the time domain signal. So again, if we look at this one, so what will be, because it's a linear operation, so we can go term by term. So what will be the inverse of 1? That means the impulse of n has Fourier transform of 1, so that means if I take inverse of 1, I'll get in impulse. Okay, again, this is 1 unit shifted impulse, so that's 1 unit shifted impulse. This is 6 unit shifted impulse, so that's impulse of n minus 6, and this is 7 unit shifted impulse, so I get this thing. So that's quite straightforward, right? Again, the next thing is to find the Fourier transform of x of z and inverse Fourier transform of x of z, such that x of z equals to log of 1 plus az inverse, and the ROC az absolute is greater than a absolute, so that means the sequence will be the right-sided sequence. Okay, so if we take the derivative of this one, so we find that okay, so just differentiate this one with respect to z, so differentiating this with respect to z in time domain will be equal to multiplication by n. So I hope this know we have done this differentiation property. So we have minus z times dx of z over d of z. So if I take derivative of this one and multiply it with minus z, so I get this one, right? Now we know that az inverse 1 plus az inverse, if I take the inverse of this one, it will be equal to a into a minus a into minus a to the power n minus 1 u of n minus 1, which is the time shifting property. Again, you have, so by using these properties we can easily find that n x of n will be equal to a minus 1 n minus 1 u of n minus 1. Or on simplification, because n is multiplied this, so if I bring it to the other side, it will be divided, so x of n can easily be found by 1 by n a into a minus n minus 1 into u of n minus 1. So we use inspection method to find the inverse transform if we know the expression is recognizable. But there are some expressions which are not explicitly recognizable. So for those, we obtain the alternate expression for x of z as a simpler terms, right? So to obtain this simpler terms, we use the partial fraction expansions. So to obtain a partial fraction expansion of x of z, so we first express x of z in the form the product of numerator and the in the product form, such as this one. You are familiar with these terms while we were doing the Z-Transform, right? So if we look at this one, these are CKs are the non-zero zeros of x of z, and dk's are the non-zero poles of the x of z. Now if m is less than n, that means the denominator has higher degree than the numerator. So poles are all first order. Then x of z can be expressed as x of z equals to summation k running from 1 up to n ak over 1 minus dk z inverse. So multiplying both sides of equation 8 by 1 minus dk z and evaluating for z equals to dk shows that the coefficients ak can be found from, right? So that's the standard procedure for finding the coefficients using partial fraction expansion, right? So ak equals to 1 minus dk z inverse of k into x of z, right? So once you multiply with this one, provided given z equals to dk, so 1 minus dk will be cancelled, and using the other terms where we replace z with dk, we can easily find the ak. We'll do some numerical example on these so that they will become easy for you, but for the up to now I think you are quite familiar with them. You have done this in mathematics also, right? Now in the case if the above condition is not met, that means the numerator has equal to or greater degree than the denominator, then we modify the equation 8 as by adding these terms, that is x of z equals to summation r running from 0 up to n, because we have the difference between the numerator and denominator degree by m minus n, because we say m is greater than n. So that's why we will use this extra term here, which is sum from 0 up to m minus 1 and br into z power minus r, and then we have the plus this one, right? So BRs can be obtained by long division numerator of the numerator by denominator, with the division process terminating when the remainder is of lower degree than the denominator. That means we will do it until we get this expression, right? That is, the numerator has lower degree than the denominator. So here long division is involved. We also have another condition where similar to previous one, the degree of the numerator is greater than the denominator, but x of z has multiple order poles. So in particular, if x of z has a pole of order s at z equal to di, and all other poles are of first order, then we can modify the equation 8 as x of z equals to r running from 0 up to m minus 1 br z power minus r plus summation k running from 1 up to n, k is not equal to I ak over 1 minus dk z inverse plus summation m running from 1 up to s cm divided by 1 minus di z of minus I into m. The BRs and AKs are obtained as follows, right? So that will be CMs are obtained as CM, right? So BRs and ARs we obtained as we have previously mentioned. The new thing is CM. So to calculate the CMs, we have CM equals to 1 over s minus m factorial minus di into di power s minus m, and d power s minus m into dws power dws minus m 1 minus diws into x of omega minus 1, provided w equals to di power minus 1. So this is the case when we have the multiple order poles. So here we have example 9. You understand that we are following the book of the Alan V. Oppenheim, I. Ronald W. Schaeffer, titled Discrete Time Signal Processing. So from this book, this is the example 9, and you understand most of the material that you have in these video lectures. They are from this book. So to find the inverse Z-transform of this signal, because it is not expressed in the simpler terms, so it's very difficult to find the inverse Z-transform of this signal. So to make things simple, let's use the partial fraction expansion that we have talked about in the previous slides to find the to make it to express it in simpler form. So to express it into simpler form, we just write x of z equals to a1 over 1 minus 1 by 4 z inverse plus a2 over 1 minus 1 by 2 z inverse, right? And this is the region of convergence, ROC, that is z absolute of z should be greater than 1 by 2. Okay, and that's the complex complex plane or the z plane. So we have two poles, right, in this case. So one pole we have at 1 by 4 and another pole we have at 1 by 2, and we have two zeros at z equals at origin. Now to express it into simpler terms, we use the partial fraction expansion. You know this equation, we have done this on the previous slide. So let's use this equation to find the coefficients a1 and a2. So using this equation, because we are going to find a1, so I write a1 here, 1 minus 1 by 4 z inverse. So dk is basically d1. So d1 has value of 1 by 4. Okay, so what we do, this says that you write 1 minus dk z inverse times x of z, and provided z equals to dk. Now instead of for k equals to 1, we have a1 1 over 1 minus 4 z inverse, and multiply by x of z. This is x of z, and z equals to here dk. So we have a1, so it will be equal to a1. Now we have two poles, so right, we have at 1 by 4, so I replace d by 1 by 4. So if you look at this one, this 1 by 4 and this thing cancels, you are left with a1 equals to 1 over 1 minus 1 by 2, and if I replace z by 1 by 4, so it will be you understand, 1 by 4 power minus 1. So if it has power, so it will be inverted, so it becomes, hope you understand that it will be basically 1 by 4 power minus 1 is basically equal to 4. So 2 ones are 2 twos are, so I get here 1 over 1 minus 1 into 2 2, right? So it will be a1 equals to 1 over 1 minus 2. So 1 minus 2 is basically minus 1, divided by 1 is just minus 1. Okay, similarly for the second part, you just replace the z by 1 by 2. So if you replace z by 1 by 2, so you get a2, right? You understand, when I multiply this thing with this, so this will cancel with this one, and you are left with this, right? 1 over 1 minus 1 by 4 z inverse. And because for the second case you replace a2 with d2, d2 is this one, so d2 will be equal to 2, and you replace z by 2. Okay, so again similarly what we have done here, again you do the same thing, and you will left with a2 equals to 1 over minus 1 by 4, right? 1 by 4, and this is equal to 2. So 2 ones are 2 twos are, so 1 minus 1 by 2 equals to basically 1 by 2. So 1 over 1 by 2 will result into 2, in fact, is it? Okay, so now you know the values for these. Now just replace the values here. So we get x of z equals to minus 1 over 1 minus, right? So because you know the z transform is a linear operation, so you can use the inspection method on term by term. Okay, so because we are given that absolute of z is greater than 1 by 2, that means the sequence is right-sided sequence. So comparing this, right, with the standard equation, if you recall that you know that a and u of n has z transform, right, equals to 1 over 1 minus a z inverse, and absolute ROC is absolute of z should be greater than absolute of a, right? So if you compare the first term with this generalized expression, so you can say basically a is 1 by 4, right? Okay, so a is 1 by 4. So because we have minus here, so that minus comes here, then a is 1 by 4, so it will be 1 by 4 power n u of n, right? So that's exactly what you get for the first term. Similarly for the second term, this is scaling, so you write 2 here, and for the rest, if you look at this one, then the a is basically 1 by 2. So 1 by 2 to the power n u of n, right? So hope this gives you idea. That's quite straightforward now. So you understand that was a difficult problem to find the inverse Z transform, but if we use the partial fraction expansion, we can express it, or we already expressed it into a simpler form. So now it becomes very right using this one. So you get this thing, and now by using inspection method, you can easily find the inverse Z transform of this signal. So in this particular example, we are going to take another case of partial fraction expansion. So you understand that in this case, if you look at this problem, it can be simplified into 1 plus z inverse power whole square, right? You can express it like this. And if you compare the powers now, here the numerator power is equal to denominator power, right? So for such types of problems, we know we have the partial fraction expansion like this one. So in this case, because they are equal, so r running from 0 up to m minus 1, so because they have the same degree, so that means m minus, they have both, so that means their difference will result into 0. So we have r equals to 0 equals, so z power 0 will be 1, and b r means we get b naught, right? So that means we can just make it like b naught. Okay, so for such type of problems, you understand we use the long division to make the uh, numerator power less than the denominator power. Okay, so what we do, we will just divide this thing by, right? So if I divide this one, I have so let's express this one in the ascending powers of z. So that means we have z square, which is the lowest, then plus 2 into z power minus 1, right, plus 1, and if I divide it, I can by this one, so it will be something like again ascending power of z, so it will be 1 by 2. If you look at this denominator, so it will be 1 by 2 z power minus 2, then we have minus 3 by 2 z power minus 1, and then we have plus 1, right? So that means if I divide it by 2, so 2 into 2 will result into z power minus 2, then again 2 multiplied by this will result into minus 3 z inverse, right? And again when I multiply 2 with 2, so I get 2. So what I am left with, these two shall stand cancel. Yeah, you know how to do division, right? So this will become minus, this will become plus. Now 3 plus 2 is 5 z inverse, and this will become minus 1. So now I can write, this is your numerator and this is your denominator. In this case, now you can see that the power of the degree of the numerator is now less than the degree of denominator, so we can write, say, so this is the plus, so we can write this one. Okay, so that is b naught now equals to how much? Plus 2, and you have this expression now. So again we use the partial fraction expansion, so you understand how we can do it. So simply we multiply x this thing, right, by 1 over 1 minus z inverse, provided z equals to 1 by 2. So in that case this will cancel, and what you get is, let me write it quickly. Right, so you understand the procedure that you have. This is x of z, you multiply, right, x of z by the first term, this one, and you evaluate it at z equals to 1 by 2. So that I write x of z, this one, multiply by 1 minus 1 by 2 z inverse, and evaluate it at z equals to 1 by 2. So you understand, by multiplying this one, this will be multiplied with, because for this part it will be cancelled here, but for 2 it will be multiplied with 2. And once you simplify all this and you replace that by 1 by 2, you get a1 equals to -9, and you get a2 equals to 8. Okay, so knowing values of these, you just put them here. Okay, so you get the expression, which let me write for you quickly. So that's the x of z expressed in summation form, simpler. Now, because you know the Z transform is linear, so when linear you can find the inverse Z term by term. So you understand, you get to here. So because the impulse of n has Z transform, right, equals to 1. Okay, so if I scale it by a factor of 2, so it will also be scaled by a factor of 2. So that means the inverse of the x of z will be the first term of x of n, that will be equal to 2 into impulse of n. How about the second one? The second term is minus, so it will be -9, right, because it holds the scaling property, because it's a linear, so it can hold, it holds both the superposition and linear property or linearity property. So that's -9, so it will be then 1 over 1 minus 1 by 2 z inverse, because we are given that the ROC is right-sided, so that means the sequence is ROC. In ROC z absolute is greater than 1, so that means it's a right-sided sequence. So for this one it will be something like 1 by 2 1 by 2 power n u of n. Again we take the inverse, or we use the inspection method for the third term also. So we have plus and 8, so that means we can straight away write plus 8. And then here if you look at this one, a equals to 1, so that means it is simply u of n. Okay, so I hope this gives you idea. Okay, so if we look at this original equation, we have the degree of numerator equals to denominator. So we have something like this, the expression for partial fraction, this condition is met, so it will be something like this one. So again, because they have same degree, so that means m minus n will be 0, so r running from 0 up to 0. So when r equals to 0, b naught, and z of minus r, so it will be 0, so we get b naught, right, which I have written here. Okay, then the next step is to use the partial fraction to find the coefficients a1 and a2, and you know how we find it. If I want to find a1, I'll write a1 equals to x of z, which is this one, multiplied by 1 minus 1 by 2 z inverse, and I'll evaluate it at z equals to 1 by 2. So because we have this expression, okay, so it will be multiplied with 2 also, so you multiply with this one also, and here it will stand cancel. Once you multiply it here, then you replace that by 1 by 2, and on simplification you will get x equals a1 equals to -8. Similarly, you go again for a2, then you multiply with this one. Okay, so for the next time you multiply with this one, you repeat the whole procedure and you get this thing. Okay, so once you do this thing, you can easily express it into sum of terms. Once you do this one, then knowing that it's a linear, so linear means you can find the inverse Z transform for individual terms. So another method for finding the inverse Z transform is using power series expansion. The basic idea in this method is to expand the given function x of z into a power series of the form, because you know that's the standard equation for finding the the Z transform. So we sum it from -infinity up to infinity and multiply it with z power minus n. So the product of x of n to the z power minus n is summed over -infinity to infinity. Okay. Now if I expand this one, okay, so because you understand I cannot expand it from -infinity up to infinity, so I say okay, dot 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 plus x of -2, x of -1, x of 0, x of 1, and this one. Okay, now once I express it like this, so I can find the inverse Fourier transform by comparing the given x of z with this one. So that's useful for the finite sequences, right? So I think when x of z is a rational function, the power series can be obtained by using long division. Okay, so I think let's do some numerical problems so it will give you a clearer understanding. So for example, we have a signal that has a Z transform equals to z square minus 1 by 2 z power minus 1 into 1 plus z inverse into 1 minus z inverse. Okay, so by simplification, okay, you just take the product of all these, so we get something like this: z square minus 1 by 2 z minus 1 plus 1 by 2 z power minus 1. Okay, so this Z transform consists of only how many terms? 1, 2, 3, 4 terms, right? So it's easy that we use the power series expansion to find the time domain signal for this. Okay, so let me write again. Okay, so I have written the equation for the Z transform. Okay, and if I expand it, okay, from -infinity up to infinity, so few terms I have written here, so they are this one. Now if we compare the corresponding terms, so we have z power 2, so here we have right, the z power 2 has coefficient equal to 1, so that means x of -2 has value of 1, so I can write 1 here. Then I compare with the second one, this is x of z, and this again x of z, so the coefficient of this one is x of -1 and the coefficient of this one is -1 by 2, so that means x of -1 has value of -1 by 2, so that means we can say x of n equals to 1 for n equals to -2, -1 by 2 when n equals to -1. Similarly, for x equals to 0, right? So z has 0 power here, so that means n equals to 0. We have x equals to 1. Then again, if I compare with x equals to 1, so z power -1 has coefficient x of 1, and here z power -1 has coefficient of 1 by 2. So that means n equals to 1, we have 1 by 2. And for the other terms, they are all 0. Okay, so that means x of n equals to 1, minus 1 by 2, minus 1, 1 by 2, and 0 for all other values. So we can also write the x of n in terms of impulses. So because n equals to minus 2, I can say this is impulse with impulse of n plus 2, which is 2 units shifted, and because it has amplitude of 1, so I can just write it as it is. Okay, because you know that we can represent any signal in terms of scaled and shifted impulses, any signal, right? So in case of discrete time signal, we can represent it scaled and shifted impulse discrete time impulses. Similarly for the continuous time case also. So again, this is x of n has value of minus 1 by 2 when n equals to minus 1. So I can say that basically this is a unit shifted impulse to the left, and it has scaling of minus 1 by 2. Similarly, this one for the original impulse, but with scaling factor of minus 1. So I can say minus impulse of n. Similarly for this one, I can write 1 by 2 impulse of n minus 1. So I think that's all for today's lecture. See you in the live session. Hopefully you will go through all these numerical problems and topics that we have covered, and we will discuss it in more details in the live session. Okay, Allah Hafiz.